This is a box that arrived this week from my friends at Tangible Interaction. And they're an interactive art group, and among other things, they have an interactive graffiti wall. So this is a thing they've been doing for a while, using these spray cans that have been modified with parts from, here's one, these like educational interactive whiteboard pens.
Scholar, the easiest way to get interactive board.
So this is a commercially available system that they've been using as a basis for their spray cans. Hey, Tuco. He's such a curious cat. Here's looks like a pen partially disassembled. He said he sent along some working units and some broken ones for investigation. So the reason he sent all of these goodies is that I was going to help him out with an investigation to see if we could improve the range on the receivers, either by modifying this kind of setup or by coming up with something on our own. Yeah, I thought this might be a good opportunity to do some of this, well, as much of it as I can on camera, and try to actually document how this stuff works and some of the process. A couple more of the receiver units. Okay, so we're back at the workbench, and I thought to start with, let's ignore the innards and the kind of partially assembled whiteboard pens, and let's start by just kind of examining the kind of outside interface to this thing. So it has two buttons here. There's also this other button on the tip. This end here is made of a kind of a shiny, thin film material, and it's got this grill that looks like it's designed so that sound waves could escape easily. So that's definitely our ultrasonic transducer. These plastic filters are actually, they look black because they're opaque in visible light, but they're actually quite transparent in IR. And I noticed that when you press these, you hear a bit of a clicking noise. And in fact, there's a microphone here. If I put this a little closer, you should be able to hear that pretty clearly on the other end. For the light output on here, we can't see that, and if we had an infrared camera, of course, the thing that's really interesting here is the waveform. And we'll take a closer look at the waveform with the oscilloscope once we get this thing apart. But one thing I like to do is just a really quick test to look at the waveform associated with some light is actually just to hook a solar cell up to an oscilloscope or an audio input. So in this case, happen to have this big solar panel handy here. And just to demonstrate with a couple of other sort of light waveforms here. So this is a little motor that I like to use as a generator. It's a stepper motor from an old printer. And I just modded it with this white LED. And so you turn it, it generates a little bit of electricity, and the white LED glows. With the solar cell, you can actually hear the waveform associated with that light. And in this case, it mirrors the RPMs of the shaft here. So if you turn it faster, the frequency goes up. So, we can use that to test to make sure that the solar panel is actually receiving signals. One other thing to keep in mind is pretty much all the light in your environment is going to have some kind of modulation to it. A lot of light bulbs produce some kind of AC content. So, there's a little bit of, kind of hum on this from the 60 hertz or 120 hertz in this light, or this halogen fixture here, and from this LED over here. And in fact, I'm going to go over here and turn up a light that has a dimmer control on it. And you can actually hear, if I pointed at that light, as I dim the light, you can hear that there's a little bit of a hum, very faint when it's at its brightest. I don't know if you can hear that. But then as I sweep it through the volume range, then you're hearing all the harmonic content from the pulse width modulation in that light. Oops. So with that in mind, let's see what this sounds like in both ultrasonic and infrared. So you hear that? So now we're getting both signals. And in fact, if we look really closely at this on the recording, we should even be able to see what those pulses actually look like, and you might even be able to see the time difference going on. All right, so here you can see a pretty good train of the light pulses on the bottom and the sound chirps on the top. So this is pretty close to the limit of what just a regular kind of sound card or audio interface can capture. It looks like the light pulses are just kind of quick little impulses, like it's just flashing the LED as fast as it can. And that's not quite what I was expecting, because it's really common for remote control type electronics to use a modulated, square wave at 38 kilohertz or so. And that's easy to detect reliably with simple amplifiers. But it looks like here, I can think of a couple of reasons why they might be using just a single pulse, if that is what they're using. It's lower power consumption than transmitting a modulated burst, and it might be it might be a much more reliable way to detect an edge. This transient here as the pulse starts, that makes a very good timing reference point. So if the receiver is using these pulses both to detect that something is happening and to start a timer for measuring the response, then it would make sense for this light pulse here to be both really short and really intense, to give a very kind of clean reference point for the timing to start. I suspect that optimizing for power consumption, they would want to make these pulses as short as possible while it's still practical to switch the LEDs on and off and actually detect them that quickly. There are two different kind of chirps happening here, and it's hard to tell with this tool, but it looks like they're at different frequencies. Like, it looks like this is a little stronger and a little higher frequency, and this is a little weaker and a little lower frequency. And it's possible that these are, this is some kind of environmental effect, like a reflection off the table. This is a super weird sort of transmitter that they're using. In fact, it reminded me of this thin piezo film. I first came across this on Parallax's website. They were selling this in their collection of sensors. It's designed as a vibration sensor, so you have some circuit board that's moving around. So this is a very thin layer of a sort of piezoelectric polymer. I think it's a PVDF. And it's mounted between conductive electrodes. I think this might be might be some kind of thin layer of silver deposition or something like that. And so, these have been around for a while. I've seen them used as sensors, but kind of one of the downsides of these things is that they're fairly fragile because of the thin film. They can be damaged pretty easily by heat or mechanical stress, and in fact, I'm pretty sure this one is damaged. Well, it's harder to tell here, actually. That looks like it might just be a piece of metal, but I've seen these transducers on their own. I'll put a picture up during editing. They're actually made using what looks like a very similar thin film process. The thin layers of plastic bonded together and electrodes kind of clamped on. Usually this ultrasonic distance measurement technique looks a little bit more like this. This is a parallax ping sensor, which is a pretty nice ultrasonic distance sensor that works using a pretty similar premise. This one sends out an ultrasonic ping on one sensor, and then it gives you a corresponding electrical pulse when it receives the reflected ping on the other sensor. And it's actually pretty easy to time those pulses accurately just using a plain Arduino or other microcontroller. This is actually an older project of mine that uses one of these sensors. This is programmed to give me a bigger reading as I get closer to the sensor. And so it's pretty sensitive. Oh, all right, now it's time to take a closer look at some of this hardware. Here's a complete pen. It's just got, the buttons and everything. And for the same orientation, here's this shell with really everything except the circuit board and the battery holder removed. So you can see on the right side here, these are the LEDs that shine through the little IR ring here. And there are actually 4 of these mounted to point in 4 different directions, 90 degrees apart. And one of them here has been removed on this board. Okay, so nothing really on the back side except for these tactile switches for the buttons. On the component side here, we have on the left side This is where the power comes in from the battery. So this is just going to be some kind of little integrated boost converter to get it up from 1.5 volts to something more usable. And the next thing that really sticks out, you see these two big inductors, and that's probably going to be part of some kind of resonant tank circuit to help the transmitter kind of boost its output voltage. The way these ultrasonic transmitters often work is they'll use the capacitance of the piezo transmitter combined with some external inductance to set up a circuit called an LC tank that kind of oscillates energy back and forth between being stored magnetically in the inductor and being stored electrostatically in the capacitor. So that oscillation actually is a really convenient way of producing sine waves in the ultrasonic range. So we can probably figure out the operation of the transmitter just by kind of looking at how those inductors are connected. So it's hard to tell on this board, but a lot of these boards have little stubs of wires on these two pads. So I suspect these would lead to the piezo transmitter unit. So let's see if we can read the number on this microcontroller. It's some kind of PIC 12F. Looks like 12F509, but it's pretty hard to read on this monitor here. Yeah, so that right there, that looks like the positive supply rail is connected to both of the positives for these two LEDs. Let's see if these LEDs are in parallel or if they're being driven in some other way. Yeah, so those aren't directly in parallel, which is good because that would be a bad idea. So this big capacitor ground is connected to the input ground. Presumably this is where the output supply voltage would end up. So let's take a closer look at the output stage driving these LEDs. So here's one just for reference where most of the LEDs are still mounted here on the left side. But we're going to be taking a closer look at this board where the LEDs have all been depopulated. The first thing I noticed was just we have this kind of squiggly trace commenting the plus together on these two LEDs. And so we can buzz that out. So these LEDs here are both wired with the plus unswitched to the power supply, and so where does minus go? And so it turns out, I thought maybe this looks like kind of two parallel drivers where we have two LEDs in series. As there's a via here linking the plus on this LED on the back to the minus on this LED on the front. So it looks an awful lot like they have these two strings of two series LEDs, and then each one has its own transistor. And so I thought, oh, maybe this pen is actually doing something more complicated, and if they're modulating the LEDs differentially based on their angle, you could actually get orientation information out of these whiteboard pens. So these two transistors are actually NPN transistors, a type of BJT, bipolar junction transistors, and they act as a current amplifier. So normally for switching a load like this, you would want a MOSFET because you would really just want to switch it on, then have as little power lost in the transistor as possible. But in this case, they're actually using the transistor as a way of relatively accurately dissipating the waste heat that would normally go into the resistor you'd put in series with the LEDs. So what they're doing here is they're actually generating a relatively small current using one of the IOs on their microcontroller and this 200 ohm resistor, about 20 milliamps. And that current flows into the base of each of these transistors. And so actually, when I thought that these were kind of two separate transmitters, then I looked into how they were connected, and it turns out the bases, this board has some gunk on it that I have to kind of probe through. Yeah, so this end of these two resistors, that's connected together. So it looks like they're just driving all the LEDs in parallel. But it would be relatively easy to modify this maybe if you wanted to kind of strobe the LEDs separately. Maybe, I don't know how much resolution you could get out of just that, but that might be a method to get some angle information out of this. All right, so I'm just going to solder some power wires onto this so we can give it some input without clips going all over the place. So yeah, maybe that's fine. All right, there's the 5-volt power supply. Nice and stable even when none of the buttons are pressed. So there's a good view of the base waveform driving the transistors for the infrared LEDs. Now these pulses are nice and short. So that is 7 microseconds. It's nice. And then 300 microseconds between the pulses when I'm holding down the tip button. Let me describe what I'm doing while the scope's happening. Let's say I'm pressing the tip and then releasing the tip. Press, release, and then the next button, press, release, press, release. So it does look like they're using the delay between pulses to transmit a little bit of information. Here's the next button, press and release. They have one of 4 different codes they can transmit using this method at least. That's nice. All right, now looking at the ultrasonic. So here I'm probing one of the outputs that would normally lead to the ultrasonic piezo transducer. And actually, I was noticing that just as I kind of touched the board, and of course I get a little bit of a tingle out of this occasionally because the voltages are relatively high. If you see the scale there, it's getting up to about 200 volts. But of course, it's a very short pulse, and there isn't really hardly any energy in here. So what you notice actually is just as I kind of move things around, the waveform changes a lot because there's an opportunity for this to create that kind of ringing resonance with any capacitance in the circuit because there's so much inductance behind this energy pulse. So just probing it like this, we're not going to get an idea of what the frequency of the ultrasonic transmission actually is, because that's going to depend on the resonance of this entire system, the combination of electrical and mechanical. So to get a better idea of what the ultrasonic spectrum actually looks like when it comes out of an unmodified whiteboard marker, we're going to come back to this thing. And actually, we'll be using an undocumented feature on it. Oh, that is beautiful. Yeah, okay, there's the ultrasonic signal if I'm just trying to hold the pen as steady as I can. Very nicely formed. So it looks like exactly 200 microseconds long. And I mean, this is not really representative of the real wave shape. It's probably pretty close to a sine wave, but this is being heavily amplified by the receiver. Great. So that's the resonant frequency, 41.67 kilohertz. 40 kilohertz is a really common frequency for these ultrasonic devices. The waveform was jumping around a little earlier, and that was actually because I was moving the pen. So here, if I hold it steady, the waveform is stable. But if I start moving it, then the point that the detector circuit first triggers kind of starts shifting up until it actually loses the wave. So right here, you see this kind of periodic pattern where we're actually seeing the wave in space. It's got kind of a difference in amplitude that this sensor is picking up. Since the whiteboard marker system is a USB device, we'd really like to see what the computer sees on the USB bus as the device identifies itself. For that, the tools you use really depend on what operating system you're on. I'm on macOS right now, so there's a tool from Apple called IO-USB Prober that I like to use to get information about the descriptors for all the attached USB devices. So the current method to find it is a little bit weird. You go to the Apple developer site, developer.apple.com, and then under Resources, way down here, you'll find Mac drivers. And then under USB, there's a way to download USB debug kits, which are packages with the USB portions of the macOS operating system, so the IOUSB family kernel extensions. It has those recompiled with debug options. So I've used these a lot in the past to get kind of nitty-gritty debug information when drivers are misbehaving on OS X. But especially recently, Apple's actually been really bad at keeping these up to date. So you'll notice the latest one is for OS 10.9.4, and I'm on OS 10.11 now. So the actual IOUSB family kernel extensions in here won't work on any modern OS X really. So what I'm actually going to do is not install this package normally, but I'm actually going to go inside and just get the IOUSB prober application, or just the USB prober application. And that's going to be, we don't actually want to install downgrade our USB stack on macOS. That seems like a bad idea. So instead, I'm just going to unextract the contents of this archive. And I think if we look in here, there we go, IOUSB prober, or USB prober. I'm going to save a copy of this. This is a handy tool. All right, and open that up. And now you can see all the crazy USB devices I have attached to the system. Let me clear out this space a little bit. So this is really the tool the pane on this tool that I use the most often. This bus probe just shows you all the USB devices attached to your computer in kind of a tree list here. So you can take each device and get a little bit of information about how that device would describe itself. So some of this makes more sense if you're familiar with kind of the details of how USB devices work. But one of the first things your operating system does when a USB device plugs in is it'll request these little chunks of data called descriptors. And the device descriptor is the first one of these. And it identifies the device mainly via a vendor ID and product ID, and then a device class that kind of talks about how the drivers should associate to that device. And a lot of times a device will have kind of a complicated class indicating that, in this case, composite means that it actually has multiple drivers, or potentially multiple drivers. But in this case, if you go a little further down, you can see that this is a standard imaging device. So this, in this case, is the camera I've been using. All right, so let's try plugging in a couple of these different receiver devices. Okay, so the first receiver device I happened to plug in here is definitely a vendor-specific device. It's showing up here as manufactured by Chang JLU and JLU DM Electronic Whiteboard. And if you look down here, it's not going to load any kind of standard USB drivers. It's claiming to be its own kind of vendor-specific device with its own protocol. But then if you look down here, the endpoints that it defines, it's only got one interrupt in and one interrupt out, set up to send 8 bytes every millisecond. So this is actually very old school to me. This seems like the kind of thing a really, really old USB microcontroller might do, where they're just setting this thing up to send these tiny little in packets the same way a really old school keyboard or mouse might do. And at this point, it's kind of hard to tell. This data could be kind of unencoded distances from the ultrasonic sensor, or it could just be XY coordinates. But either way, they're going to have a driver that kind of takes apart these packets and actually simulates mouse movements or whatever else they do with it. The next one I plugged in is also a JLU DM electronic whiteboard. This is one of the kind of long bar-shaped units that says Scola on the top. Yeah, it looks pretty much the same. Okay, so far I have these three that all seem to come up with the same USB IDs. Here's one that is in the same enclosure but has a sticker on it labeled driverless. So yeah, this is definitely a new model. This has a different name, HID Electronic Whiteboard. So if you're not familiar with HID, that's a reference to the Human Interface Device Standard. So this presumably can work with normal drivers and shouldn't require whatever driver or translation the previous models are using. This HID descriptor should tell us kind of what sort of input device this is emulating. And yeah, this one knows how to be a mouse. So this is saying, yeah, it has some buttons. Yeah, digitizer. So this is going to act like an absolute position mouse device. So it gives you XY coordinates. That's cool. Yeah, here is the HID-based whiteboard, and I just got out the pen, and I can already get mouse movement events, just moving the pen around on my desk here. So yeah, if I hold down the front mouse button, then that looks like it's a drag. If I use the tip and kind of drag it on the desk, that's also a drag. If I press the other button, that's like a right click. Presumably there's some difference between the tip and the front button that I just am not noticing by dragging rectangles on my desktop. So it looks like the manufacturer's website is currently not working, but there's an archive, thanks to archive.org. And yeah, this actually illuminates some of their product lines. So it looks like this Bowwing 1 was their first generation. And that's the one that I have several of. And here's the Bowwing 3, which I have a few of. And as far as I can tell, they consider the kind of driverless and the kind of vendor-specific versions of their USB device to still be kind of the same product. They're definitely externally pretty much identical. But architecturally, I suspect that most of these used the same kind of microcontroller guts inside up until that HID version, which happened somewhere inside of this product line. So once I found this, I tried looking around for drivers, but you know, like none of these links actually work except for lyrics. I think that might be subtitles for this video, which is an incomplete download, but then the software downloads are completely broken. So after doing a quick search for drivers online and coming up empty, I fired off a quick tweet to Alex, and he got back to me right away with the software they're using, which also happens to be for the first generation firmware in these electronic whiteboard markers that uses the vendor-specific protocol instead of the HID protocol. This is the driver package that just has some kind of software-based solution to emulate a mouse. So that's actually what I'm interested in looking at next. That will give us an opportunity to look at the USB protocol and just see what those little 8-byte packets actually look like, sort of in the wild. That seems unlikely. That seems very unlikely. Yeah, I think this installer is just not happy. Well, here's some of the individual packages. Let's assume that driver is probably the first thing we want. Okay, so this little EWB driver program, which was buried inside of the electronic whiteboard package, this just seems to be a little headless daemon that just communicates with the whiteboard device using Apple's user space IO USB lib interface. So it doesn't seem to have much of a user interface, but if we just run strings on it even, we can see some calibration messages in here. And then IO USB device right here is the name. I mean, these names are all things that you would expect to see in a user space program that communicates with devices using Apple's user space API. So just on a hunch, let's see if even just running this process is enough to see some communication with the device. So I have it plugged in through a hardware USB analyzer. Rather, I have it set up so that I can plug it in just a second. It's actually not plugged in yet. And if I start capturing, all right, now I plug it in. So, oh, this is great. So right away, this stuff up here is the hardware in the USB hub, or in the USB host, detecting what speed to use. And then we have the operating system doing its usual descriptor probing. But then right away, this in transaction here, so these two are already kind of vendor-specific things. So I cheated, and off camera before I'd found these drivers, just reading from this in endpoint to see if the device would just speak without having to really configure it at all. And I wasn't so lucky there. So having the driver, now we see that there's this little command where the driver sends an out to that output endpoint, which was also a little 8-byte interrupt endpoint. And it has this 1 byte hex 52. And then after that, now we see an in with 52. So that could be some kind of reply. That looks suspiciously like it could be a version number or a flag of some sort. And then these NAC packets, these are USB protocol indications that the host keeps asking whether any data is available on this in endpoint, and nothing's available. So that tells us two things. It tells us no data is available, so this is probably not going to transmit until it detects a signal from the pen. And then this also tells us that, well, now the host, in this case my desktop computer, knows that it should be listening for data on this in endpoint. So that tells us that this driver does indeed seem to be kind of running and asking the pen for data. Now I've got the pen here. I'm just going to start pressing. Oh, there we go. We immediately start seeing some data here. I forgot how to make this auto scroll. Here we go. That's great. So if I'm just pressing a couple different buttons. So it looks like the button identity is in that first byte. So if I just hold down the front button consistently, this is holding down the button closest to the tip, and I'm just going to move it slowly. So these values are already kind of pre-processed, and they could be kind of distance metrics. They could be actual pixels. I don't yet know whether the calibration on this unit is done, in hardware or in software. Well, in firmware or in the desktop software. I saw a video. Alex rather sent me a video of the calibration procedure on the newer HID-based devices, and that one actually just involves. Well, we could try it here. That calibration procedure was to hold down the rear button with the transmitter very close to the receiver until it beeps. And so I don't see that happening here. So I suspect that kind of holding it down until it beeps thing is oh, that's interesting. So I just noticed actually that as I'm moving this around, I am actually getting mouse clicks on my computer, but they're all in the top left corner of the screen. So that's another evidence that the calibration in this case is actually done by the desktop software, and so that would kind of lead us to suspect that this data is kind of pre-filtered insofar as it's not going to be generating more data bandwidth than a regular input device would, but the coordinates here don't seem to be converted into pixels yet. And so this EWB driver thing on its own, without having been installed correctly or anything, doesn't seem to know how to convert the coordinates into the right space. So aside from this first out packet here with the 52, I haven't seen any other outs. So I suspect what's going on is that this is just turning it on, or possibly a combination of turn it on and also reply with version information. It does seem like in the in packet, they're using this first byte as a combination of a kind of button identity and a packet identity. So here, the first byte is changing based on what button I've pressed or whether it's a button press or a release. And then up here, the first byte, suspiciously matches the byte that was sent out. So it seems safe to assume that this is a reply to the command to start, start operating, or exit low power mode, or begin streaming data, or whatever this actually does. And it's possible they've just taken that as an opportunity to also send back version information, because that would be a convenient place to store stuff that maybe is finer grained than what they wanted to put in the standard USB descriptor. So I'm sure the folks at Tangible have already been down this path with reverse engineering the protocol and making their own driver, since that's how the interactive spray can works. But I still thought it would be interesting just to try writing a very simple Python program to just dump out the raw data that the hardware is giving us to get a better idea of what that looks like. So I wrote this simple script using Python and the PyUSB module. So it starts out just finding and configuring the USB device, and then it writes this 52 packet that we saw that seems to enable something necessary for the device to function properly. And then afterwards, we can just tell the computer's USB system to poll for incoming packets on that interrupt endpoint. This is actually not a great example of how to read data from an interrupt endpoint, but it'll do for this example. All right, so let's just start this. So after playing with this for a few minutes, I think I've got some idea of what the numbers in this packet are for mostly. So that first byte is definitely a packet type identifier. It looks like 9, 10, 11, 12 are for all the button press, release, and move events. So 9 seems to happen when you press the tip button. 10 is any button released, and 11 and 12 are these buttons. And that next byte is usually 0, but occasionally I see a 9 there. I don't know what that's about. Now, it's possible that's reserved for kind of hover detection that maybe isn't enabled in this mode. Then those next two numbers are 16-bit, and so that second one behaves a little weird when I'm close to the receiver and kind of hovers around 240. And I think that's some kind of anomaly. Normally, those next two values are pretty comparable, and it looks like those are distances for the two ultrasonic receivers, or, times. So they get smaller when I get closer to the receiver, larger when I get farther away. Also, when I get close, that second value seems to be kind of anomalous and just stick at 245 or so. But the left value still works, and in fact, I can kind of home in on that left ultrasonic receiver, and it can get down to almost that same level, around 200. That's interesting that when that one gets so low, the right receiver seems to start working. It's interesting. I wasn't sure about these last two numbers at first. They're both 8 bits. Then I noticed if I just move the pen back and forth between the two, you see them kind of increase and decrease in turn. So my guess is actually that the two 16-bit numbers are time measurements, and the two 8-bit numbers are power measurements. And as far as I can tell, it's just measuring the power of the ultrasonic signal. The LED is either, it receives it or it doesn't. This is the one in the new all-in-one enclosure, but still with the old kind of pre-hid firmware that uses the custom protocol. So this looks fairly similar, with the exception that those last two numbers don't seem to work the same way they did in the other model. We still seem to be getting the same codes for the first digit, the first byte. And that second byte is still usually 0 and sometimes 9. Then we have the two 16-bit codes. Then with this model, the last 2 bytes seem to always be 1 and 94 as far as I can tell. Let's see if this one does anything special when I hold down the back button while holding the pen near it. No, nothing special. It doesn't seem like there's really any significant kind of surface wave effects going on. This is really just looking at the waves going through the air. Okay, now that we've examined these receivers from the outside a bit, I have the soldering iron and the tiny screwdriver. Specifically, let's see what the differences are between these 3 versions. So I have here on the left the first generation in 2 parts, and then these 2 are both in pretty much the same container. This is the newer one that supports HID directly without any sort of vendor-specific drivers installed. Alright, we'll start with this one, which is the oldest and probably the most broken. So, there's not a whole lot to see before we take this can off, but right away we can see the sensors at least. So on the right and left here, these actually look more like kind of typical PCB mount microphones than the usual kind of ultrasonic rangefinder style metal can sensors. And these diodes are weird. I've never seen photodiodes mounted quite like that. Little tantalum up here to filter the input power. All right, let's get these cans off. These are not actually a through hole, it's just surface mount soldered. Yeah, no components under that. They just really need to shield the photodiodes. So I suspect that the sensitivity of the light sensor is really one of the bottlenecks in this system. So they have to really crank up the gain on those amplifiers, and because of that, just totally shield the heck out of this thing to prevent radio interference or 50 or 60 hertz hum from mucking everything up. So we should have some op-amp goodies under this top cover. Yeah, this is really not tacked down super aggressively. Almost like they wanted it to be easy to get into. Like they were having trouble with it at first. Oh, there we go. Already greeted with some good passives there. Ooh, very nice. 3 separate channels, it looks like. So these are all MCP 602, which is a dual op-amp for microchip. A pretty run-of-the-mill gain bandwidth product of around 3. So they're not going to be able to do a whole lot of gain on each of these, but it's a pretty good budget op-amp. So the 3 photodiodes are actually wired in parallel. They're just summing the current. You can see one leg. You can see one leg pretty clearly on this side. It's harder to see on this side, but you can see one trace kind of behind the shield here that looks like it's connecting the other side of the diodes in parallel. So it looks like they would just be trying to, get all the photons they can, sum that into a current as much as possible, shield out all the electrical noise, and then just amplify that as much as they can with a moderately priced op-amp. The pinout should be pretty easy to work out. So we can right away see 2 pins that are joined to the ground plane here. And then just looking at the wiring, one's the shield and then one's a separate ground wire. But they're both joined to the ground plane here. It does look like they put power on the red wire here. You can see that leading to the plus side of this capacitor over here, the 10 volt 4.7 microfarad. So that just leaves 3 more pins, which presumably would be the output signals. So the right ultrasonic here goes to orange. It looks like yellow is the IR signal. And then that leaves, brown going to this ultrasonic. Well, that's pretty straightforward. Alright, so with the analog front end out of the way, let's see what's in this kind of auxiliary microcontroller beige box that goes with that unit. Now, this is the nastiest, cheapest plastic case. Not like it really matters, though. Alright. Wow. This is spacious. So this brings back some weird memories. This microcontroller is a PIC16C745, which is actually one of my kind of old buddies. This was the first thing I learned how to program USB on. It was really old school. No working C compiler, really. All assembly language, terrible bugs everywhere. Wow. This fill is actually a very fine mesh. This is a really strange board. I just looked closer at a few of these chips. So it has some familiar analog jelly beans. Got an LM393 over here. Had a few op amps I had to look up. So this one's an MCP4201. And then here I've got a TI part, an LMB324. And this is a really strange board. It's got this very gritty ground plane, lots of vias connecting everything. Over here, this amplifier section, it has all of the passives very carefully spaced out in a grid with this ground fill around it. So it's a very strange analog design. It'll be interesting to see what they changed in the later revisions. And of course, over here you can see this like empty RF module location. I think they have some other products in their line that communicate wirelessly, and they're just powered over USB. All right, next we're opening the one that seems to be, from a software perspective, very similar. Cool. Open. That's interesting. I don't know what these little black nubby things are. If that's part of the plastic case, or... let's find out. Looks like this is just press fit in there. Lightly restrained by the USB connector. Cool. Wow. Those are the photodiodes. I haven't seen diode packages like this in ages. Really tall, kind of like it's like a TO92 transistor, but kind of elongated. Let me zoom in. Yeah. You can see they have options on the board for mounting another style of photodiode, but this one's so cool, why would you not mount this? Similar arrangement on the other side. So hardware-wise, this looks pretty much the same, like it might even be the same schematic pretty much, but just organized into a line instead of into two boxes. So I had kind of tossed aside this enclosure earlier, but actually this has some interesting features here. So you'll notice it's got these magnets, which I guess help it stick to the whiteboard. But it's also got this nice copper plating. And I think this might actually be a real layer of real copper kind of sputtered on there. So it's actually quite conductive. Switch this to resistance. All the way across that, it's like not even an ohm. I'm curious actually how this makes contact to the ground on the PC board, because for it to be kind of a nice Faraday bubble around the sensitive amplifiers, this would need to connect to the amplifier's circuit ground. So I'm guessing that's what this little plated hole here is for. So that's clearly making good contact when the circuit board's in. So that's really nice. That's really a nice way to shield the board. Just copper plate the plastics and then make good contact to the board. And of course they only bothered to copper plate the one side. Alright, now let's take a look at the newest one here, the one labeled driverless. See if it's at all the same. Nice. Same copper plated enclosure here. So right away here we've got a brand new component. This guy is probably their buzzer to make the noises for the automatic calibration or the built-in calibration routine. So this is interesting. The microcontroller situation has drastically changed. Instead of that one really ancient PIC, now there are two PICs. So we've got a PIC 16F883 over here and then a PIC 24 over here. That's interesting. This U13 is new. Is that a voltage regulator or something? Yeah, right there you can see the markings on it. So that is a Dallas one-wire temperature sensor. Comes pre-calibrated. So that is probably a new addition on this board to help them better calibrate for the difference in speed of sound due to temperature changes. Maybe they had some teachers complaining that their calibration had to be redone every time the temperature in their classroom changed. So I'm not going to go super deep into the analog in this video, but I'm seeing a lot of the same parts here, and it seems likely that the circuit is similar. Alright, so the USB is going to this microcontroller. That is the PIC24? Yeah. These seem to be some kind of serial bus connecting the two processors together. So yeah, these 3 resistors are all 100 ohms, so probably series resistors just to prevent prevent stress on the GPIO drivers if these two chips decide to fight each other. I just noticed all these nicely labeled factory test points. These look like the kind of things they would use to check out all the analog circuitry during manufacturing, but it might be really fun to have a probe around at these. So we've got these kind of indiscriminately labeled T1 through 3 over here. And then we've got ultrasonic left and right, IR left and right, and it looks like these different test points might be the inputs and the outputs for the amplifier, possibly. We can take a closer look. And also interesting, these 3 wires here are the serial bus going between the 2 processors. And then right below it, these 2 wires are USB. So you can see the USB going over here, then through these series termination resistors into the PIC24. So the PIC24 is the one doing all the HID emulation. And then this little PIC 16F883 down there is probably programmed as some kind of auxiliary device to do the actual sensing. So it's possible that's just going to be like a nice I2C or SPI peripheral that we can use separately. So this is pretty neat. Let's get this powered on and take a closer look. So I don't know if there's something wrong with the design or whether they're just really pushing the limits of the length they can get out of these USB cables, but man, this is garbagey. The USB analyzer is showing just tons of dropped packets, and the mouse is working regardless, but that's really not pretty. Okay, a little bit of probing around has helped shed some light on the seeming redundancy of the test points here. So there are actually 3 IR test points and 4 ultrasonic test points, as well as these 1, 2, and 3. And it looks like these square ones, TPIR, TPR, and TPL, are kind of the most amplified signals, potentially the ones that are going right to the microcontroller. Down here with a little bit less amplification, we have separate signals for each of the 2 photodiodes. And then we also have slightly less amplified versions of the 2 ultrasonic signals. So I'm going to just solder some wires to the more amplified test points so that we can get a more stable view of those signals. Oh, that's interesting. So here we have on the top trace, that is the TPIR test point, and on the bottom trace, that's TPR, so the ultrasonic sensor on the right. So right away we can see the ultrasonic inputs also respond to the IR signal. There's a little bit of crosstalk between the amplifiers, it seems, which is not too surprising and not a big deal since we know to wait a bit before looking for the actual ultrasonic signal. Alright, so here are the light pulses. And of course the thing that really should matter is that the timing on that leading edge, which seems, pretty stable. The duration of the pulse does change a bit depending on the signal strength. So here I'm just kind of moving the pen around. As I get it really close to one of the photodiodes, the pulse gets a little longer. And as I move it away, the pulse kind of gets more normal sized. So, the microcontroller probably isn't using that, but that might be available as sort of an amplitude sensing mechanism. Alright, so if we look a little farther over, now we actually see the ultrasonic waveform. I think I can actually hear see my voice in that waveform. Test. Oh, nice. So now I've got 3 probes on the scope. We have the external trigger connected to the IR test point. Then both of the amplified ultrasonic test points, TPL and TPR, are going to the scope. In case you can't read the scale on the scope, that's 50 microseconds per division. And so mostly we're just shifting the phase of that initial onset of the ultrasonic signal. But there's certainly some really interesting harmonics going on as the signal bounces around. It's pretty cool. Oh, hot stuff. We got 3.3 volt logic. Oh, this looks like some kind of packet on the middle pin. But only when it's plugged into a computer and I'm pressing a button. Yeah, that looks like that might just be a serial port. 19200. Cool. So it looks like the serial data sent back by this secondary microcontroller is all synchronized with the IR light pulses. So the IR comes in, then presumably this is about where the ultrasonic pulse would show up if it was on this trace. And then we've got this packet, which looks kind of familiar. Alright, there we go. There's the serial data, little 8-byte packets going from the little PIC to the bigger PIC. So I think these values coming over the serial port are actually kind of uncalibrated ultrasonic values. So I'm noticing that as I get close to this sensor, that second 16-bit number is getting small. As I get farther away, it's getting larger. The second number is also getting larger, but to make the second number really get small, I've got to get near the other sensor. Or rather, the first number. So now the first number is small. Now the last two bytes aren't changing. It's interesting. Alright, that was fun. I think that's deep enough into this particular rabbit hole to go in one video. We've uncovered plenty of opportunities for hacking these things, from making your own transmitters, making your own receivers, to speaking the USB protocol to the older receivers, to using either the HID protocol or this kind of hidden serial port in the newer receivers. If you're working on something that involves kind of position tracking on a flat surface, then maybe this is something that could be adaptable. If you like this video, it would help a lot if you gave it a thumbs up, and if you want to see some more of this kind of stuff, then definitely check out my other videos or even subscribe, and you can be the first to know when something new comes up. So thanks for watching, and I'll see you next time.